What that means is as you reach the end of the disk and you come back, okay, you should have large enough holes that you can continue this. Okay, otherwise, if you have one block here and one block here, you'll write a block here, then you will do a seek and write something there, then you have defeated the whole point of doing block structure. Right, yes.
For garbage collection, does that simply involve updating the super block?
Okay, so what does garbage collection mean? So that requires us to go into a little more detail. So what you are going to end up writing are not blocks, but they are segments. A segment is a collection of blocks. Okay? So let's say each segment is 5 blocks. Okay? So let's say you basically write out a segment. Okay? Now as you write out, so your segments are written contiguously, okay, and they are long. So now when you reach the end of the disk and you come back at the beginning and you start writing the log again, there will be some segments that already have valid data. You can't do anything. You have to skip over them. But if there are segments that have sufficiently large number of deleted blocks, okay, blocks that are marked for deletion, what you will do is you will do garbage collection, which means if let's say 2 out of the 5 blocks are valid, you will take 2 blocks and write them somewhere else and empty the entire segment. So now you can write to that entire segment contiguously again. Okay? So this is how garbage collection would work. I mean, and this is garbage collection on disk, unlike languages like Java that do garbage collection in memory. Okay? So what this means is periodically in the background there's a garbage collection process that is running, that is just moving data blocks around to create new empty segments. Okay? So that's additional work that the file system has to do. Even if there is no reads or writes coming in, you still have to run garbage collection and move data around. Okay? That's an additional overhead on the system that you have imposed because of this log structured organization. Okay? So you can do this at periods of low utilization. In the night you can run garbage collection and reclaim enough contiguous storage space that you can then write out new segments contiguously the next time. Okay. So this is essentially what a log structured file system does. Okay. It's another file system that was designed from Berkeley back in the 80s, okay, or I think early 90s, where they realized that your file system better be optimized for writes because most of the traffic that are going to disk are actually write in there. Doesn't mean there are any reads. Every time there's a cache miss, there will be a read and a seek, but predominantly it will be write based. Okay, so you are optimizing it for sequential writes. Any questions on this? Okay, so if you combine the two together, okay, so last time we talked about striping, okay, which is here. Okay, so essentially your entire disk set of disks across machines. So remember in XFS this is a distributed file system. So your disks on different machines. Okay. So what you are going to do is you are going to basically write out a log, but you are going to stripe the log. Okay, so if you have blocks of the log, you are going to say this is block 1, block 2, block 3, segment 1, segment 2, segment 3, and then you compute a priority, and then you store this on machine 1. Segment 2 is stored contiguously on machine 2, segment 3 on machine 3, you store a priority. So this is network striping of the log. Okay, this is basically a striping your data across disks, and that is, as you can remember from last time we said, that's RAID organization. So you have redundant segments called parity, just so that if a machine goes down or a disk goes down, you can use the parity to reconstruct that segment. Okay? So you are combining a log structured organization which was designed for a single disk. Okay, the original LFS was just a single disk file system. Here you are generalizing that to multiple disks. And the way you do this, you take the log and you stripe it like you stripe a file in RAID. Okay? And then you actually use network striping to stripe them across machines. Okay? So this is the two put together. So now you can see that in XFS there is no single server. Your blocks are scattered across machines. Okay? To retrieve a single file, you might have to send a request to multiple machines on your LAN and get different blocks of the file, okay, because the blocks are all striped across machine. So there is no single machine that's a server. A set of machines collectively store all the data from the file system. Okay. So that's the main principle of XFS. There are other details which I'm going to ignore here because they're not important from this discussion perspective. Any questions on XFS? Okay, so I'm quickly going to talk about one final file system, and then we are going to move on to the World Wide Web. And this one is called Hadoop Distributed File System. Okay, so if you have used MapReduce or Hadoop or any of these data processing frameworks, you will know that the data is typically stored on a distributed file system called HDFS. Okay? This is designed with completely different goals in mind. Okay? So first of all, this is designed for what is referred to as big data processing. Okay? Reading or writing very large data sets, processing it to compute some result. Okay? So you might have very large log files or all kinds of other files, data collected from sensors. You want to run a computation on it. Okay, there's a lot of data here. The data set tend to be hundreds of gigabytes or terabytes in size often. Okay? So you want to use a cluster of parallel machines to read a lot of data in parallel, do some computation, and then maybe write intermediate results or whatever else you need to do. Okay? And the framework to do this is called, in this case, there are many different frameworks, but for HDFS, this is called the MapReduce framework. So there are two phases, a map phase and a reduce phase for computation. Okay, we will not go into Hadoop or MapReduce. I just want to describe what the file system is. Okay. So first of all, you need very high throughput in this case, because each of the applications or jobs that run process large amounts of data that's stored on the underlying file system. Okay. So these are basically some design goals that HDFS has. So you need fault tolerance, obviously, because you are storing your data across machines. If any machine goes down, you need to make sure you can still retrieve that data. Okay? You need the ability to read lots of data in parallel. A large data set scales to hundreds of nodes. Okay? In this case, they made an important decision, which is they assume that data does not change once it is written. Okay? These are large data sets that you are collecting. You basically store it. Typically, you will not go and change that data. What might happen is you might read that data, compute some new intermediate versions or post-process versions of the data and write it back. Okay? So this is essentially called worm environment, write once, read many. Okay? So this is basically files are assumed to be immutable, okay, which means you create them, you don't change them once you create. Unlike a general purpose file system, you can update a file. Here, this file system is not designed for that purpose. Okay, you simply create files, okay, and then you can read them as many times as you want and compute other results using that file. Okay. So that simplifies many design decisions. Once you write it, you don't really have to do it. Okay. And then you will have to ensure that the data and computations are matched. Okay. And I'm going to show you a picture here just to give you some high-level idea of how this works. Okay. So the main there are several key ideas. One key idea is there is a separation of what is called the metadata management and the data management. Okay. Metadata is data about the data. Okay. This is in a Unix file system, inodes were metadata. Okay. In this case, there are entire machines that all they do is metadata management. Okay. So if you say, I want to open this large file, okay, let's say it's 1 terabyte data set you created of log of some sort. You first go to the metadata manager and say, where are the blocks of this file stored? Okay? And all that the metadata management does is it basically keeps track of index for each file. Okay? It says this file has 10,000 blocks, each of this block is replicated 3 times, block 1 is replicated on these 3 nodes, block 2 is replicated on these 3 nodes. So all of that information is just kept on this metadata nodes. Okay? That's all they do. They don't actually store any data, they only keep metadata. Okay? And then you have data nodes, which are going to essentially keep blocks of the file. Okay? Every block is basically going to be stored in all the files. And this is your distributed file system here, where you have lots of machines, they will all have disks, and then there will be chunks of the file that's going to be stored. So you will take a large file, you will chop it up into chunks. Okay? And because this is high throughput, the chunks of the blocks are going to be of large size, okay? Megabytes in size. Typical file system block sizes are in kilobytes. 4 KB is the standard block size that is used by a typical file system. In HDFS, the block size, the default is I think 64 megabytes. Okay? And 64 megabytes because typical files are assumed to be in gigabytes. So you can afford to chop off this very large file into 64 MB or 128 MB chunks, and each chunk can then be distributed across. In fact, each chunk by default is replicated 3 times in HDFS. Okay, every 64 MB file, block or chunk as it is called, you create 3 copies and you store it on 3 independent nodes. So even if one node goes down, there'll be 2 more copies in somewhere on your file system. Okay? So you can control the degree of replication. Okay, the default is 3. Every chunk or every file is replicated 3 times. Okay? And so essentially this metadata manager will tell you every chunk which machines are they stored. Okay? So you will take a large file, you chop it up into chunks, create 3 copies of each chunk, store it on 3 different machines, take the next chunk, repeat. Okay, and then essentially you're going to keep all of the data. Yes.
With the large block size, how do they control internal fragmentation?
Okay. Question is, with the large block size, how do you control internal fragmentation? So internal fragmentation is going to only exist for the very large chunk, last chunk of that data file. Okay? Because if the last chunk only needs maybe 1 kilobyte, will still have a 64 megabyte chunk allocated. The assumption is that the data set is large enough, the files are large enough that fragmentation is the price you have to pay. Okay, it is going to waste some space in the very large last chunk of the file. Okay. Any other questions on this? So in any case, if you have actually used map reduce processing or anything like that, I hope you will have encountered HDFS, so you will have some sense of what I'm talking about. So externally it just looks like a normal file system, okay? Except that files are very, very large and you have lots of machines storing them, and internally you will replicate. Okay? Notice here you did not use anything like RAID or anything like that. They chose a much simpler policy saying let's keep 3 copies of every file. Disk space is cheap. You can get a terabyte size disk for $100 literally. Okay? So why bother doing anything like RAID? Let's make 3 copies. And that was their philosophy. Now there is something more to it than that. Okay? So the point here was you do not want to have parity computation to slow things down. Okay? So they chose to actually trade storage space for performance in some sense. Okay? So, and they assumed that rather than keeping 2, 3 is actually a good enough number for to handle even 2 failures, concurrent failures, and not lose any data. Okay. So those were all design choices that were made in HDFS. I'm not going to go into more details of it. I just wanted to give you some sense of a file system that is designed for very large scale data processing. Okay. Typically you wouldn't go and store tiny files like a 1 kilobyte file on this file system. That would be a complete waste of space on this file system. You store very large files, and that's what is designed for. Okay, so let's skip down the storage systems. So we are going to change gears a little bit and move on to the next chapter, which is going to be on the web. Okay, so this is a new chapter in the book. I'm going to quickly review some of the material that we have covered in various different lectures. Okay, I mentioned search engines, I mentioned web browser, web client, and we are doing threading, and so I'm going to go through that quickly, but focus most of the remainder of the lecture on things like HTTP and SOAP, and then eventually web caching. And so that's really what we want to get. Okay, so let me give you some very quick. So I'm going to first 5 or 6 slides. I'm just going to go through quickly because we've gone through this previously. So most of the web, as you know, relies on a protocol called HTTP, Hypertext Transfer Protocol. It's a request response protocol. Clients, typically could be browsers or some other applications, send a request. It's an HTTP request. It goes to the server. The server might retrieve your data from disk or from a database or whatever else it stores the data, constructs a response and sends it back. Okay? We will look at what HTTP does in just a few slides, but that's basically what you need to keep in mind. Okay? You have many kinds of clients. I've shown this before. This is what a typical browser application looks like. Okay, most browsers are actually complex applications. They are multi-threaded, but there are multiple components. There are things like components that communicate or are responsible for network communication. Talk to web server. You might have clients that interpret. Okay, if your file actually has JavaScript embedded in it, you have to actually run a JavaScript interpreter in your browser. Okay, it will actually run that JavaScript program and then compute some result. Okay, you might have to have parsers. So So you can parse HTML or XML if it's embedded in your file and so on. Okay? And then you have the rendering engine, you have the GUI, which is all of the user options that you show the user and so on and so on. There are many different components to a browser, which we don't really need to go into here, okay, but just keep that in mind. Okay? And then come to the proxy moment. The same is true of the server. Server has many different components as well. Okay? What this picture is showing, it looks complicated, but it's really showing you the architecture of the Apache Web Server. Okay? It's a very popular open source web server, widely used. Lots of websites that you interact with actually run on Apache, okay, which is a HTTP server. And the way Apache is built is it's a highly modular web server. Okay? There's a core Apache server which is called the Apache core, but a lot of the functionality is configurable. Okay? You can basically, when you have a configuration file which tells Apache when it starts up what modules to enable. Okay? Different modules will enable different kinds of functionality. There may be modules to do things like PHP processing. There may be modules to implement caching. There may be modules to implement SSL, which will enable you to create secure connection. So each of these components is actually a module so that you can pick and choose what you need for your server. Okay? You don't have to get a very large bloated server which has 1,000 functions where you only use 2 features. Okay? You can enable the features you want and then basically get a browser server that's compact enough. Okay? And what this is simply showing you is depending on which modules are enabled, it uses a notion of a pipeline request processing internal. Okay? Request comes in, here are different modules, so you basically, each module that is enabled, you basically hand the request to it, saying, okay, go process it, that will do some partial processing of that request, and it will move on in the pipeline. Okay? So basically, each module gets some chance to process part of that request. Okay? And then that's how request processing is done in Apache. Okay? Long time back when we were talking about threading, okay, I told you that Apache uses a statically allocated thread pool. Okay, when requests come in, you basically take an idle thread, you hand it a request saying go process it. Okay, so that thread is essentially going to go call functions using the hooks in each of those modules. Okay, and then once it's done, then that thread will go back to the idle pool and that request processing will be done. Okay, so that's just something to keep in mind. Okay, other to map onto. Okay. And then I have already introduced the notion of a multi-tiered web architecture as well, where I said that there are, typically this shows you what is called a 3-tier application. Okay. Tier 1 in this case is HTTP, is web processing. This is a web server. This is typically called the app server, that's the database, okay, or where the data is stored. Okay, when requests come in, the web server does initial HTTP processing and hands off the request. Okay, so this is basically how requests arrive. So they come to the web server, they're handed to the app server, which is where most of the application logic resides. Okay, this could be written in many different ways. Okay, this just shows you one of the many. This shows you a CGI bin where the application is actually a script, okay, that is called. You can write your application in PHP. You can write your application in Java if you use Tomcat or J2EE server. You can use Ruby on Rails or Python, Django. In that case, the application app server is either in Python or Ruby. Okay, so there are many different choices of how you write your web application. Okay, depending on what you have done, that is what is going to sit here on this second tier. Okay, third tier is typically the data management tier. Okay, it's typically a database of some sort, which is where data resides. Typical request might actually involve making a query to the database, retrieving some data from the database, constructing a response and sending it off. Okay? So for example, if this is an online store, okay, you basically send in a search query saying this is a bookstore, I want all books that match this keyword. Okay, so your request is going to come in and that request is going to essentially trigger a query into the database. You might search your product catalog and say what are all book types that match this query. You get some responses, you take that response, you construct a page on the fly, okay? And then that's an HTML page, you hand that off to your HTTP server, so the replies go backwards. Okay, request is processed, okay, in the forward part, it comes here, then here, and then responses trickle backwards, and then they're sent back to the client. Okay? So these 3 tiers machine depending on the size of your web server, the website. Okay, so if this is all, if the most common case is you basically run Apache, you run some sort of an app server, and you have a small database that all reside on a single machine. Okay? If you have this, then the typical acronym that you will see being used for something like this is called LAMP. Okay, that's just an acronym. It says Linux, Apache, MySQL, PHP. Okay, Linux is your platform, Apache is your web server, MySQL is your database, and PHP is the app server that you've written your thing. Okay, this is all industry acronym, not a technical acronym. And that's what you will hear saying run your app on a LAMP stack. LAMP stack simply says that you basically take those pieces of software and put it on a machine and you run your application. Okay, but of course you can use very different things there, not just those 4. What does CGI stand for? CGI is basically Common Gateway Interface. Okay, before you had PHP and all of this kind of stuff, the standard way you could actually do something more than just retrieve a static HTML page was to write a script. Let's say you write a shell script or a Python script. Okay? So request would come into a web server. The web server will literally start a new process and ask the script to run that request. Okay? So that was done through this gateway interface. Request would basically fork off a new process, and then you could run a shell script with the right argument. The shell script would return some results, and then maybe it queries something and returns the result, and then you can. That was the old clunky way of writing web application. It required you to fork off a process every time a request came, which was expensive. Okay. The modern way is, of course, not to use CGI scripts. You can use PHP or Python, and then as an actual server that is continuously running. You don't start a new process every time. Okay. Any other questions? Okay. So the book is a bit dated, so it still says CGI. So here is a way you can cluster your web server. Okay. Large websites will often not run on one machine. Okay, they'll be running on a cluster of machines. Okay, and here what would happen is you would have a front-end machine which is called the load dispatcher switch. Okay. So this is basically going to expose an IP address to the external world. Okay. All requests are going to arrive at the front-end node. Okay. The front-end node will do many things, including load balancing. It will use things like dispatching. Okay. So whenever a new request comes in, okay, there will be a set of these back-end nodes. Okay. And remember that each of them could be a multi-tier, okay, logically shown as one mesh box. Okay, but that could be each a multi-tier application here. So there could be the 3 or more servers there. Okay. But let's just assume they are one logical box for our purpose. They are replicated, okay, just to scale up capacity. So whenever a new request comes in, the front end has to decide which of those replicas is going to service your request. Okay. You could implement a very simple round-robin load balancing policy, which says every new request, send it to server I+1 mod n. Okay. So you basically round-robin. That works in many cases, not always. Okay. If your requests are part of a session, okay, simply blindly forwarding every new request to a next server is not going to work. Okay? Because when you have a active user session, your session may have state associated. Okay? Think of you visiting a website, okay, let's say it's an online store. Okay? You go and you basically take a product and put it into a shopping cart. Okay? The state of the shopping cart is a session that one of these servers has maintained. Okay? So let's say the previous request where you say add to cart was serviced by server 2. Now next request, let's say you click buy. Okay, and then the buy request comes in, you send it off to server 3 because you're doing round robin. That's not going to make any sense because that server has no state of your session. Okay? The session state is actually stored on the previous server. Okay? So you might actually have to keep track, okay, not just do plain vanilla load balancing, but keep track of sessions, saying for each session, once you map it onto a server, all subsequent requests of that session have to be sent to that server, because that server is keeping state of that session. Okay. So your front-end node gets quite complicated because it has to keep track of session state which sessions are mapped onto which server. It still has to do load balancing, but load balancing is at a session granularity, not at a request granularity. Each new session can be assigned to any new server. But once you assign it, all requests from that session until the session closes have to go to that server. Okay. So all of these things are actually being handled by your front-end switch. Okay. So it is not just a very simple load balancer, it has to keep track of all these other things as well. Any questions on this clustered web servers? Okay, so there are some more pictures of this. I'll show you another picture. Same picture as the previous slide, just shows more components, which is not really informative, but here is your front end. You can know it's called a load balancing switch, sometimes it's called a dispatcher, and sometimes it's called a front end node. They all by and large do the same thing. And the question really, what that next slide is showing is when a request comes in here, how is that request actually forwarded to one of those servers? Okay, so there are one of two ways to do this. Okay. One is what is called an HTTP redirect mechanism. Okay. A redirect simply says when a request comes in, you basically redirect it internally to another server and you handle it. Because the entire HTTP request is sent off to another server. Okay. That's one way by which a front-end node can just hand off a request that has come into another server. Okay. Another way to do this is the front-end switch will actually receive the HTTP request. Okay. Then it will set up a new HTTP connection to whichever web server it wants to forward that request to, and then simply send that request over on a new HTTP connection. You basically take the same request and it will be sent off as if it's a new request. And so then the first request and the second request, these are two TCP connections, they are connected. Whatever is coming on the first request is relayed onto the second one, and the replies that are coming back are sent back on the previous connection. Okay? So this requires having two independent TCP and HTTP connection, one between the browser and the switch, the second between the switch and some one of these servers. Okay? And then whatever is coming from the browser is basically simply copied from one connection to another. So you just receive and then you send on the other one, because you basically logically connected them, they look like single connection. Okay. So you might have to do this kind of stuff. This is called TCP splicing. Okay, you take two TCP connections, you splice them together. Okay, in the literature. But so there are fairly sophisticated things that the switches do, okay, which I will not go into any more details here, but you get the sense of kinds of things you have to do to make all of this work. Any questions on this? Okay. So with that very quick overview of some of these concepts that we had encountered a while back, let me now get to HTTP and so. And typically you can use HTTP is basically, think of it as basically a file download protocol at some level. A long time ago you had FTP, you could just connect to a server and download a file. HTTP is basically that with more descriptive features. Okay, so for example, you can use HTTP to obtain a text file from the server, an image, audio file, video file. You can download an entire application. You can download content which are multiple different types. Okay? So they are all MIME encoded, okay, because you have to deal with all of these kinds of content over the same protocol. Okay, essentially it uses an encoding called MIME, which is a multimedia encoding format. This is how you also send attachments to email. Okay, you can send all of these things through email as well. So the standard way is you encode all of this in using a standard encoding called MIME, which allows the other end to interpret what has come. Okay, because you might send an HTTP request, the response might be in JPEG image. The response could also be a video file. The other end needs to know what kind of content it is in order to interpret it. All of that is encoded using this MIME type. It says this is the what has come is a MPEG movie or a JPEG file, or it's an HTML file and whatnot. So then you can interpret and parse the content accordingly. Okay. So this is the various kinds of web documents you can retrieve. Okay. All of them are retrieved over HTTP. Okay. What is shown in this picture is a browser which is running on this client, okay, accessing a server. Okay, typically what you would do, you will send off a request and get an HTML file. You will then parse the HTML file. If there are embedded JPEG images or some other objects in there, you are going to set up new HTTP connections to download each of them. Okay. Those embedded objects may or may not reside on that server. Okay. Okay, if that's, let's say somebody's embedded an ad into a file, okay, the ad server may be a completely different machine. You have to go to the ad server and fetch the ad. Okay, but let's say the simplest case, you might have embedded images that are on the same server. Okay. In that case, you are going to set up new HTTP connections and retrieve other content, and then you will take all of that and render it and display it to the user. Okay. So what that is telling you is retrieving a single HTML file and its embedded content may involve multiple HTTP connections. You want to get the HTML file, then you parse it. If there are images, each image will require a separate HTTP. So there will be many different connections that get established. So this is showing 3 different connections that have gotten established between the client and the server. That might waste some overhead because each HTTP connection is a separate TCP connection. Okay? So you have to do all this TCP handshake, all of that has to happen. If you remember when I was talking about TCP, I said there's a 3-way TCP handshake. The 3-way SYN messages go back and forth. There's a FIN. There's a lot of overhead that is involved in just setting up a TCP or an HTTP connection with TCP. Okay. So what HTTP did, this was what HTTP version 1 did. What HTTP version 1.1 did was to say, let's not waste overheads by our resources by setting up multiple connections. Why not just have one connection between the client and the server? Let's make it persistent, which means that as soon as we retrieve the image, let's not tear it down, because the browser might send more requests. Okay? User may click on a link that may trigger yet more requests to the server. Okay? So rather than setting up a new TCP, HTTP connection and thus a TCP connection over and over again, let's just keep one. Okay? And let's just use that to send multiple requests and get multiple responses. This would be more efficient than setting up n connections because there are n objects being retrieved from the server. Okay? So what that will mean is after you have retrieved, after you have gotten a HTTP response, you will keep the connection alive in anticipation that the user might send yet more requests. Okay? And there will be some timeout value. If no new requests go from the user or the browser, after a while the connection will be torn down. Okay? But you will not tear it down immediately, just to save on some overhead. So what you don't want is something like this, where there are lots of connections getting established and wasting overheads. Resources, creating overheads. Okay? So this is what is referred to as HTTP 1.1, which allowed this notion of a persistent HTTP connection. Okay? Very recently, as of the last year, okay, there's a new proposal for HTTP called HTTP 2.0, which has come out from Google and a few companies that want to further speed up this notion of HTTP and its performance. Okay? I won't go into that here because it's not yet completely rolled out. Some very advanced browsers support HTTP 2, but many web servers still don't. That's something that's coming. It just further improves performance by adding more features like this that will help you improve the performance. Okay, you want fast loading times, that's what user care about. Okay, so it further improves the performance using other tricks, which I will ignore here. Okay. But let me tell you a little bit about the protocol itself. Okay, so any HTTP request can be one of these 5 kinds. Okay. The most common one is a GET request. Okay. GET simply retrieves a web page or an image. Okay. So typically when you make an HTTP request, so let's say what you have is let's say you basically are so let's say that's your HTTP request, and then the server name and some object and directory. So what happens is then in the HTTP server will set up a connection to browser will set up a connection to that server and send what is a GET request, which will, in this case, we simply get index.html. Okay? That's telling the server that the browser wants this file. Okay? This could be basically a long thing saying, let's say, if you actually go to our courses web page, say courses 677. So that's a path name followed by some object, which could be a file or an image. Okay, so these are GET requests that simply retrieve some content. HTML files, JPEG images, movies, all of these are basically. This is the most common kind of a GET request. Okay. The next most common kind of a request is what is called a POST request. Okay. A POST request sends information from the browser to the server. Typically, it's used when you submit a web form. Okay. If you fill out a form in your browser and hit submit, that goes back as a POST request because you're not trying to get anything. In fact, you're sending information which are fields of a form filled out back to the server. So basically, you use POST to send data back to the server. You use GET to retrieve. Okay. There are other kinds of requests which are not that common. You can actually use a PUT request to actually, it's opposite of GET. You can upload files to the server. Okay. Typically, servers are not going to accept arbitrary files from browsers because users are untrusted. But there are ways by which if you're a web developer and you are actually updating content, you can use PUT to update you or upload new files to the server. Okay, just as FTP allows you to download and upload, so does HTTP. Okay, this is disabled by default for normal users, okay, because you can't just start uploading garbage to any arbitrary web server. That's not allowed. But if you're authenticated, you might be allowed to use that function. Okay. There's also delete, which allows you to delete. Again, that's only allowed for authenticated users, not for any arbitrary users. Okay. So GET and POST are the most common. There's also head, which allows you to just retrieve the head of the document. We'll see how that is used in caching in just a little bit. Okay. So these are typical kinds of HTTP requests that you will see. Okay. So now with that, let me say a little bit about other uses of HTTP. And typically, the most common use is users are using browsers to go visit some web pages and do something. Okay. But that's not the only use of HTTP. There are many scenarios where the client and the server are both machines. Okay. In the typical case, the client is a user, a human, who's using a browser to access web content. But there are many cases where both endpoints are actually machines. Okay. So in this case, you have what is shown in this picture is a client machine making a request to a server machine and is using HTTP as a way to do RPCs. Okay. So you can use HTTP mechanisms to actually make RPC requests. Okay. And this is basically and if you do this, you have constructed what is called a web service. Okay. In this case, the server exposes an API. Okay. The client actually uses that API to make requests or get content and so on. Okay. And that API is actually running over a standard HTTP protocol. Okay. So if you do this, you have this notion of a web service, and you'll see there are many things here that look very familiar to us. Okay. So you'll see the client is actually an application. It's no longer a browser. It has a stub. Okay, very similar to when we talked about RPC. We said you write RPC request, the stub code is automatically generated. Okay? And then there is the communication layer. In this case, the communication layer is actually using HTTP. Okay, all the requests and responses are being tunneled over HTTP rather than a vanilla TCP connection. Okay, if you use RPC or RMI, it's just using a low-level TCP connection for communication. Okay? Here you are using HTTP for communication. Okay, and you can use, just as your IDL in the case of RPC, you have web service description language to describe. Here is the API that this web service exports and so on. Okay. So a lot of complex applications are written as web services. Okay, so you might have batch jobs that run every once in a while, then they basically talk to a service and whatnot. Okay. So think of an automated order processing system. Okay. Let's say at the end of each night, there is a program that looks at a store inventory. Okay. And for any items that are low on stock, it automatically places an order for more items to arrive at the store. Okay. Things like that run over as web services, where let's say the manufacturer or the distributor has a web service which allows you to do ordering. Okay. Here, rather than humans using a browser to place an order, it's a program that's making the orders based on whatever is low on stock. Okay. And it's going to send those as RPC requests that run over HTTP rather than somebody sitting at a browser and ordering things. Okay. That's just an example. There are many such examples as well. Okay. So I'm going to go into a little more detail into some of these. Okay. So I mentioned this protocol that's being used as tunneled over HTTP. Okay, that's called SOAP, okay, which is an acronym for Simple Object Access Protocol. Okay. It's a way to actually tunnel RPC responses using a SOAP language, a protocol. Okay. And essentially what it is it is an XML description, okay, which basically encodes a request and arguments. Okay, or it could be, in this case you can see that this is basically a request to send an alert to a user. Think of, let's say you have a calendar. Okay. In the calendar you put an appointment or an alert, and at that time you're expecting to get an alert on your phone. Okay, saying this is, so in this case it's a reminder to maybe pick your daughter from school at 2 p.m. or something like that. So that is basically going over SOAP. In this case you will see the command name is here. Okay, it's called alert control, which is the program that's actually going to push that alert to a phone. Okay, that's it. Okay. Here is the argument to that command is here, which is essentially a string, which says this is basically what you have to say. Okay, so you essentially have the name of the request, you have arguments that are all part of this. Is essentially an XML document. I don't know if anyone knows what XML is. It's a markup language, like HTML is also a markup language. And XML is more structured than HTML, but it looks very similar. Okay, so you will see there's a body and a header and all of that. Okay. So this is an example of an XML-based SOAP message. Okay. That is just to give you some sense of what it looks like. Okay. Let me give you some examples of how you can use it. Okay. So typically, this is how SOAP is a web standard. Okay. Just as HTTP is a standard, SOAP was designed by the World Wide Web Consortium, the W3C consortium, as a way to write web services. But it never really became popular. Okay, there were some applications that were written with it, but it's too complicated, so people actually didn't use it. But I'll show you some things that did get kind of out of this question.
I've used SOAP kind of a lot from Microsoft's WCF. And something I've always wondered about is for that URL that is being called on, so like example.org/alert control.
Yep.
With WCF at least, they're all hosted on the same domain. So it's just like tiny.org or whatever / like the name of your method.
Yep.
How is that resolved? I just don't understand how that could possibly be. I don't know if that's an appropriate question, but
no, I think it's not an inappropriate question. So think of this as when you submit this request. This is very similar. What has to happen is very similar to what happens when you click on a link in a browser. Okay. Let's suppose that was, instead of thinking of this as XML, let's say you had a web page open. You're a human. You had a web page open and you had a link which was essentially pointing to that. So if you clicked on that link, how would you go and resolve it? The same is true of when this message is called. Okay, how would you resolve it? So what would happen is you will basically go and you will extract the server name, and you parse that XML, you resolve the server name, call DNS, find the server, connect to it, and then try to send a request to that URL.
okay, I think my question was more like if you have two people who are working at like two different companies and they both write a method called alert control, are they going to be on the same URL in the same path?
Oh, no, I think so. Your question is different. So there has to be a server domain somehow as part of this, right? You are asking, can two independent companies write an RPC message with the same name?
Well, I mean,
you could, but you will still host them on different servers.
Yeah, it just seemed like, in my experience with SOAP, that doesn't seem to do that. I don't know, I'm just confused about that.
No, I think, see, the issue is each of those requests will have to go to a specific server that recognizes. So if you write a buy service, and some other company writes a buy service, they are on two different servers. You host your code on some server, they host their code on some server. So as part of this, you have to have some server information there. Just because you might actually have a shortcut which just says /alert doesn't mean that the server is missing. It is either in some config file that says by default connect to this server. There has to be a configuration somewhere and tell you that. Otherwise it won't make any sense. Okay? So here you have a full server name and a request, but you can leave the server name out. But it will result to a server that's configured somewhere. Any other questions? Okay. So this is SOAP, but as I was saying, SOAP is actually a heavyweight protocol. Okay? It is designed for machine-to-machine communication. In fact, it is designed for a completely distributed system where n components of an application all talk to one another. Okay? And because it has that notion of multi-part group communication, not group communication between components of a group, it is more heavyweight than the typical case where there's a client and there's a server. Okay? It just so happens that in more of these cases, the client and the server are applications, not a browser and a human and a server. Okay? So what this has actually, the way it has gotten used is this notion of Restful Web Services, which is a much more simplified version of what SOAP actually was designed for. Okay? So so REST in this case stands for Representative State Transfer. It's yet another acronym that you will see. Okay? So it uses much simpler versions of how HTTP is. So for example, REST will use HTTP GET to read some data from the server. Okay? Again, this is like calling RPC-like request. Okay? Post is going to allow you to create, update, delete. You can use put and delete as well. Okay? It is simpler than RPC style SOAP, but it is much closer to the web. So most of the services that you will see today, okay, actually expose REST API. So if you have Google Maps, okay, if you want to embed Google Maps into your web page, you have to actually make requests to Google Maps saying, show me a map of this location and so on. So Google Maps service actually exposes an API. Right? You can send it a request, okay, saying, show me the map. You can specify GPS coordinates, saying this is a latitude, this is a longitude, then it will show you something. Now that is going as a REST request. Okay? Same with most other services. So you can actually write your own social media client to connect to Facebook or Twitter or whatever. They are all exposing you an API where you can say authenticate and then show me the feed for whatever this is, and then you can specify some arguments. Okay? The web browser is simply using these mechanisms to actually display to you the same content so that it looks like a normal web page, but internally all of these are APIs that are getting called. Yes, question.
How is authentication different in RESTful versus SOAP?
How is authentication different between RESTful and SOAP? Both have to have authentication so that the server knows you're asking for content that you are allowed to access. Okay? The authentication is going to be depending on whatever the server chooses. If it's a password style authentication, you have to specify username and password. Okay? So the first of these requests will actually have to authenticate. And then once you're authenticated, you will have a session. That's an authenticated session, then you can make this request. Okay, same is true in SOAP. So that part does not change. The specific requests might change, but you still have to use some notion of authentication. Any other questions here? Okay, so these are all called web services, which allow you to make requests. And here are some two examples of the same service that you would have written in SOAP and with REST. Okay? And all this is doing is it is connecting to, let's say, a server to retrieve a stock price of some company. Okay? So in this case, so you essentially you are basically asking for the stock price of IBM. Okay? Here is how the SOAP request would go. Okay? So you would connect to some server and its stock service, /stock service, and the argument you will provide is IBM, saying, so you connect to that service and say, send me the price for this company. Okay? So the name of the company is an argument to the service. Okay? In a RESTful service, you essentially have a URL where the arguments are encoded as part of the URL. So essentially, you're just doing get/stock_price/IBM. Okay? So you are essentially connecting to the server and sending this URL, but that URL is going to trigger a request to the service, okay, which will retrieve the same stock price. So there are just two different conventions of how you actually make the request and how you pass the arguments. Okay. The other thing to keep in mind is RESTful web requests are much more compact than SOAP requests. Okay, here your entire XML, so that's your HTTP request and the entire XML is in the body. Okay. Here the header itself has content that you are trying to retrieve. Okay, so essentially your get has all of the information that you need, and then that's just the server that you're connecting. Okay. So it is a much more compact way of making the same request of the same server, and that is basically what has become popular. If you write a program to connect to any web service that has any APIs, you will be basically most likely doing this. Doesn't mean that SOAP is not used, it is, but it is less popular than RESTful services today. Okay, so if you have any web service that exposes an API, more likely you will go down this way route than that route. Yes.
What's the S colon for in the XML? It's like S colon quote or S colon.
This one?
Yeah.
I think you're just saying that's the request. Okay, so you're talking about S colon quote, right?
Yeah. Or tickets and other stuff.
Yeah, I think that's the service. S just stands for the service here, and I think I'm just saying that's the ticker symbol, so you're just giving different field names. The naming convention. It's taken from the book, actually, they didn't explain. I'm guessing. Okay, any other questions here? Okay, so here is the reply to both of those requests. And I'm not going to go into the details here, but in both cases, you're actually going to get back the price of IBM, which is embedded here. Okay, so it says stock price is 45, and that is, I think, for the, that's the SOAP. Okay, that's the RESTful one. They look similar when you get the response. Okay, but we won't go into too much details here. Just keep in mind that SOAP, sorry, that's the SOAP call, and then the RESTful call was not shown. But here is just a single slide that gives you some differences between SOAP and XML. Okay. SOAP essentially is designed to be language, platform, and transport agnostic. SOAP is not, doesn't have to run over HTTP, can run over other protocols. Okay. RESTful Web Services are actually designed to run over HTTP only. Okay. You cannot change the underlying protocol. SOAP is not designed, it's a web standard, but it doesn't actually depend on HTTP. It runs by, in many cases, on one. Okay. This one is, as I said, is designed for general purpose distributed computing. You can write an arbitrary application. You could take your lab application and use SOAP to implement it. If you have N parties or NPFs, you could have written it in all in SOAP. Okay. RESTful Web Services are client server. Okay. It is specifically designed for one client making a request from a server. Okay. You cannot have two clients interacting with one another and with a third server. Okay. That's not what it is designed for. Okay. This one has standards like WSD and UDDS. They're all written as standards. RESTful is basically not standard based. That has become the de facto practice. That is how people write applications. There is no standard that says you have to write it this way. Okay? But it has just become accepted practice. Okay? If you have written Ruby on Rails or Python, Django, any of that, that's actually underneath using RESTful Web Services. Okay? And as you imagine, you have wide design latitude in how you construct your application. There is no one right way. Okay? So essentially, it's kind of roll your own. You design it the way you want. Okay? This one is error handling, extensible, it's also heavyweight and so on. That is much easier to learn because I've simplified it. Okay, it is tied, heavily tied to HTTP, as I said, and it is concise. So those are the differences. This is how the designers of the web thought things should be. Okay? This is how they are. Okay, because they decided to make things more complicated than they had to. Okay, so that was sort of the takeaway. Yes.
When you say heavyweight, is that performance as well as just development, or is it mainly just developing and working with it?
Both. So if you see here is basically just to get one number, like what's the stock price, you're getting that bigger response. So you can think of the overhead is high. Okay? Writing that service will entail similarly high overhead. You will have to write an interface definition, run it through a compiler, then the compiler will generate stub code, you will link it and so on. Okay? If you written Python Django code, you can just write some 10 lines of Python code and get something simple up and running. So there's a lot of difference. Design, development, performance, network overhead, all of that is higher because it was designed for a more general case. It's not that they were trying to do something bad. They just thought that they should do it for a more general case where arbitrary groups of machines will talk to one another. Okay, the common case is one client is asking for something from a server. Okay, so that is why that one is much easier to write. Okay, so in the remaining 10-15 minutes, I'm going to talk about caching, which is the last part of our web chapter. Okay, so this is web proxy caching. So here is basically where we are going to come back to go from a client server architecture to a client proxy server architecture. Okay? So we are going to assume now that there is an entity that is sitting between a browser and a server. Okay, so you have you will have your client. So rather than client directly sending request to the server, they'll send a request to their proxy. Okay? The proxy may decide to service that request by itself without any further interaction with the server, in which case a response comes from the proxy, or the proxy can talk to the server and then get back a response. Okay? So we are going to look at this notion of a client proxy server architecture. That's number one. The most common use of the proxy is to put a cache. So you can cache frequently accessed web pages at a nearby proxy. Okay? So let's say you put a big proxy at the UMass gateway router. Okay? It caches all the web pages that are being accessed by users. Okay? If your popular websites, okay, it is likely that many users are all going to that website frequently. If you already cached content, recently accessed content from that website, if a new request comes in, you don't have to go all the way to the server to fetch it. You can essentially get the content from a local proxy which is right within your domain. Okay? This will substantially improve your performance. Okay? That's how a web proxy caching is typically used to accelerate the performance seen by end users. Okay? The problem though is if you are actually retrieving a web page that is cached locally, you better make sure it has actually not changed at the server. Okay? Because if the web page has changed, then you are going to get stale content. Okay, so with any web caching, you have to ensure you have consistency, okay, which is what we are going to talk about in just a moment. Okay, so caching implies that you're going to get performance benefit, but also consistent. Okay, so what is shown here in this picture is not just one cache, but there are multiple caches. Okay, so you'll see that there is a web proxy here, there's a web proxy here, there's a web proxy here. Okay, there are 3 web proxies being shown. And then whenever a client connects to their local web proxy, okay, if the content they are requesting is not cached at web proxy, it's showing this principle of what is called cooperative caching. So rather than fetching it from the server, you can ask other nearby proxies saying, do you actually have this page? Right? If so, you fetch it from a local proxy rather than going to the server. Okay? So in this case, you will see that request came in and it was essentially a cache miss. Local cache miss. So you ask 2 other nearby proxies, so do you have this page? If they had it, then you would have gotten it from a nearby proxy. In this case, neither of them happened to have it. So then you send it to the server saying, send me a copy of this page. Okay. This is called cooperative web caching. Okay. Set of nearby caches all collaborate to service requests. Okay. And the idea is, if you don't have it locally, but another nearby proxy has it, it may be still faster than going to a remote server. Okay, so this is referred to as cooperative caching, which we are going to talk about in just a minute. Okay, so but let me show you the same picture I drew here is the picture you should keep in mind. Browser without a proxy would directly go to the server, get back a response. Here you have a web proxy cache that's sitting between the browser and the server. Okay, so we are going to look inside this. And I should mention that proxies are used for many different functions, not just caching. Okay? Another important use of proxies is what is called transcoding. Okay? To transform your web content on the fly. Okay? The most common case of transcoding is to actually take a video and then lower the bit rate. Okay? So for example, if you are accessing Netflix on your phone, okay, it has a much smaller display than if you are accessing it on your large TV. Okay? So there is no reason for you to receive a very high bandwidth, high definition version of that file when you're going to display it on a small screen. Okay? So what a proxy might do is take a high def video and transform it on the fly to fit it on a small screen where the quality is adequate. And it might save some network bandwidth because you don't have to send a high bandwidth video on the network if you are accessing it on a small screen device. Okay. So that's another use of it. The third use of it is you can actually transform web pages as well, not just content, You can take a web page that is formatted for a desktop on the fly, reformat it so it fits well on a smaller device. It's another use of transcoding. Okay. Here we will not talk about transcoding, we are going to talk about caching, but keep in mind that there are many uses for a proxy. Okay. So let's talk caching. Okay. So consistency basically says that web pages are going to change over time. Okay. If there are caches that keep a copy of the web page, how do you ensure that the content in your cache is current, is fresh? Okay, that's the problem of cache consistency. Okay. So here we'll use web proxy caching as a way to understand how cache consistency is implemented. Remember when we were talking about consistency, I talked about models. I just said this is more abstract. When we talk about web, I describe how these are implemented. So we are going to see a sequence of different approaches. Okay. So there are several different ways by which a web proxy can actually ensure the consistency of its content. Okay. We can, as we'll see, use a push-based method or a pull-based method. Can use what is called an update-based method or an invalid-based method, and any combination of the four. Okay. Now, what you have to keep in mind is the method is going to the best. There is no one method that's going to be the best one. Okay. That is going to depend very much on the kind of content you are trying to access. Okay. And what you have to realize is different web pages are updated at vastly different frequencies. Some web pages are highly dynamic in that they change very frequently. Okay. Any web page of any leading newspaper may be updated every few minutes. Okay. At least there will be a breaking news section in that web page which will be updated every few minutes. Maybe other content changes every few hours. Okay. And then you might have web pages that are, let's say, people's personal home pages that may be updated far less frequently. Okay. Maybe once a week, once a month, okay, or even less frequently. Okay. So you will have very different update rates. Okay. Depending on the update rate, different cache consistency mechanisms might be more or less useful, okay, as you will see. So let me first describe the high-level approaches, then we'll see which ones are used in what scenario. Because first, let's talk about a push-based approach. Okay. In a push-based approach, okay, it is the responsibility of the web server to ensure that content that's kept at the proxy is up to date. Okay. What that means is every time you basically update the content on the server, okay, you basically go and update your web page on the server. Okay. The server will then send a message to every proxy that has cached that page and either send it the new version of the page or it will send it an invalidate request saying the page has changed, so delete the version that's in your cache, invalidate the version that's cached. Okay. So essentially you have, whenever the web page changes, there are two kinds of messages the server will send to the proxy. Okay. One is called invalidate, that just says discard the object from your cache. The other is an update which says here's the new page. Okay. So there are a few different things here. Okay. The first is the server has become stateful. The server has to track for every web page it hosts, every single page it hosts, what proxies out on the internet have cached a copy of that object. Okay. So that if your page changes, you can send them appropriate messages, either an invalidate or an update. Is that clear? Second, okay, so in addition to being a stateful server, the server has to decide if a page changes, which of those two kinds of messages to send. Okay. Should you send as invalidate or should you send an update? Update will send the whole page, a new version of that page. Invalidate just says, here's a URL, okay, discard that content for that URL from your cache. Okay, so which one could you send and for what purpose?
Smaller, then you can just send a new version.
Okay, so you can make a decision based on size. If the page is small, why not just send the entire page? Yes.
If you have limited bandwidth, it might be better if you control the rate at which you send the object versus maybe getting a flood of requests all at once.
So you can decide based on the network load. The load is high, Why send large pages? Okay, it consume more network bandwidth, send a small invalidate message. Okay? So you can make a decision based on size, you can make a decision based on load, you can also make a decision based on popularity. Okay? If there are popular pages, okay, if you send an invalidate, that message will invalidate the content in the cache, but soon thereafter a request for that web page is likely to show up at the proxy because by definition this is a popular page. And then the proxy will then request the server for the page. Why not just send it right away because you know that a request is going to come soon after. You can do the work now and just send the page. Okay? On the other hand, if it's not a popular page, why waste overhead and send a page to the proxy when it's unlikely that it might ever be accessed? Okay? So you can decide based on popularity. So all of what has been suggested are actually techniques that might be used to decide which of the two to send. Okay? So there's the two things to take away are it's stateful, because you have to keep track of which proxies cache it, and you have to decide whether to send invalidate or update based on the content, the type of content, size of content, etc. Okay? So that's what is listed here. Okay? But the other good advantage of this approach is provides you good consistency guarantee. Because as soon as the page changes at the server is going to send out some requests, okay, off to the proxies. Okay? This will ensure that the time for which a proxy has stale content is as small as possible. It is limited to the network propagation time for the message to propagate from the server to the proxy. Okay? So it is not strict consistency, but it is close. Okay? It is very tight consistency. Okay? Because as soon as it changes, you start sending things. Okay? So this is basically the server push based approach. Okay? Next time I'm going to talk about the pull based approach. We ran out of time, so we'll stop here. Okay? And just one more thing I want to announce before you all leave. I am thinking of having an extra class this Friday. Okay? Because in the last week of classes, that Monday I'm traveling, so I cannot teach that class. So to do that, I'm going to have a makeup class this Friday. Can I have it at the same time on Friday this week? Does anybody have any major constraints? I will of course record it and all that, so if you miss it, you can still watch the recording. If you have strong objections, email me before I go and announce it. Okay, I'll announce it later today. All right?